In the unclustered tree index, we have the same tree structure, but the index file is separated from the data records file. So, the data records file does not have a specific order of records, but the index file holding data entries has pointers to the data records following the tree sorted structure. The same assumption of 67% page occupancy also applies here, meaning that the index file pages are at 67% occupancy. One more thing. Remember that the index file data entries do not hold the full records. For our estimation purposes, let's assume the size of the entry kept in the index file for each data record is 1/10 of the actual data record. Using these assumptions, the scan of the heap file using the index file is going through the leaf level of the tree index and fetching corresponding data record. This is going to give us the records in a sorted order. Reading all the entries of the index file will take 0.15b times d plus 6.7 RC. This comes from the number of leaf pages being 0.15b and number of data entries in a page being 6.7 R, following the occupancy and the size of data entry assumptions we had. However, the expensive part in this operation is fetching each record for the data entry in the index file. Since the index is unclustered, there is no guarantee that records are on closed pages. Therefore, the cost will be loading 1 page per record, and therefore BR times D plus C. If we remove the negligible parts from the estimation, we can estimate the cost of a scan with BD times R plus 0.15, which is quite high. Note that the data records file can be sorted with 2 passes, which takes 4 times B. Therefore, sorting the file is a less costly alternative to scanning the file to get the records in order. So, if you want to do the scan, maybe sorting is better than using the unclustered tree index. For cost of search with an equality selection, using a similar logic to the clustered B+Tree file and the 1/10 size of the data entries in the index file, the cost of locating the page with the data record is D logarithm of 0.15b to base f. Then we need to find the record in the data page, which, given the same logic of binary search, 67% occupancy, and data entry size being 1/10 of the data record, could be estimated at C times logarithm of 6.7 R to base 2. Finally, there is a need for a page read from the data file for getting the data record, which adds another D to the equation. Multiple qualifying search results are not guaranteed to be on the same page. Therefore, if more than one match is available, each would need another IO. For search with range selection, the first page is found similar to equality search, and then one IO needs to be performed for each of the records matching within the range. Remember, we said that scanning through the unclustered tree index was expensive, right? When the range to cover in the search with range selection is large, covering the records in the range follow the same rule. So, when the range covers considerable number of matching records, it might be less costly to perform the search using the sorted data record file. Inserting the scenario involves inserting the record in the heap file, then inserting the data entry in the index file. The cost of inserting into the heap file is 2D plus C. as we have seen earlier in the cost estimation of the heap file. For inserting the data entry into the index file, it takes a search to find the right leaf, then one IO with cost of D to add the new data entry. For delete, we need to find the data entry in the index, which has exactly the same cost of search. Then we need to write the modified pages in the index file and in the data file. This will have cost of D for each, adding another 2D to the total cost of delete.